Hi student. Uh, Now I would like to explain the application of DAC that I have already shared with you, and with some diagrams that I have already explained previously, with the concept of DAC, that means digital to analog converter. And today I will explain the one of the most important application of DAC, that means digital to analog converter. That means the generate a square waveform using DAC, right? So how to generate a square waveform? Not only square waveform, it may be a ramp function, it may be a staircase waveform, it may be anything, any kind of waveform from any digital input, with the help of the DAC can be generated by using a program code, by using the concept of DAC with the help of 8255, and obviously with the help of the interfacing part of 8085, right? And today I will explain that how it works and how it is generated, what is the program code, and what is the logic behind that, and what is the concept of or the role of the subroutine call in the program, right? Okay, so before going to the main programming code, I have once again explained over here the DAC 0800 and the interfacing part with 8085 via 8255. Right, I think that everyone are able to recall that part that I have already explained in my previous lecture. At the one day lecture, it was a DAC, and in that lecture I have already explained that each and every function of the pins of these the nothing but these LM741, that is nothing but the op-amp IC, and it is equivalent to the I to B converter, that means current to voltage converter, right? And what are the individual pins, what are their functionalities, everything was explained. Please go through that video before going to the application of DAC. You must have the knowledge of DAC to get understand the application of DAC, that is how to generate a square waveform using DAC, right? Okay. But most of the applications, the architecture of DAC will be same, so that's why I have used over here the DAC 0800, because it is the most simple and convenient method to use for the application part, right? Okay, so this is nothing but the DAC, in the interfacing of DAC to the 8085 via 8255. Okay. Okay, so now my today's objective is to generate a square waveform, right? Because you have already used to generate a square waveform using a CRO, using MATLAB, because if you know the MATLAB very well, it is a 1 minute function to generate any kind of waveform by using a simple code, right? But today I will explain the hardware implementation, and by uploading a programming code, that's why to generate a square waveform, but with the help of this DAC, right? Because our input is analog sorry, input is digital and the output is analog. The digital pins is this one here, the 8 pins of there, and for 8 pins interfacing part we have used the port A. I think the port A, port B, port C are well explained in case of the 8255, so please go through this. I have used over here the port A for giving the input, right? And the corresponding data will be generated by using this DAC, corresponding analog waveform, right? Okay, so this is your square waveform, nothing but the square waveform. And where the and what is the explanation of this waveform, what is the objective, how to generate? This is nothing but the amplitude axis, this is nothing but the time axis, right? I think everyone are used to do this notation. And there is some waveform of there, there is some waveform, this is blank, this is again, this is 0, this is 1, this is 0, this is 1, this is 0, right? So blank portion will be treated as 0, and the wave portion will be treated as your 1, right? So these 1 and 0, so this is your complete waveform, right? And the time duration of each and every pulse from the blank portion is your T by 2. So half of the time period, so the total time period is your T, right? The total time period is T. So half of the half of the time period is used for generating the 0, and half of the time period, the rest half of the time period is used for generating the high voltage. Not only this one, it can be maybe 2, 3, 4, 5, everything, but the corresponding the voltage we can generate by using the formula, and that I have already explained in the later portion, right? Okay, so this is nothing but a square waveform. Means there is a edge, rising edge, there is a falling edge, rising edge, falling edge. But the rising edge voltage, this is a corresponding value of the voltage, because this portion is always treated will be 0, but this portion can be the voltage of plus 2 volt, plus 3 volt, plus 5 volt, but this will be generated by using the formula. I am once again telling over there, right? Okay, so this is a square waveform, has the 0 voltage output for 1/2 period, and a voltage Vt that I have treated over here, the voltage Vt in general notation, but this voltage can be replaced by 2, 3, 5 or any value, right? And Vt for another half time period. That's why I have written over there this T by 2 and this T by 2, though the total time period is T, right? Now this is a very important portion that I have very well explained in your PDF portion, that is the how to generate this square waveform by using this 8255 and 0800 and your 8085. Okay, because we are using 8255. So 8255 has a control word register. I think you are very well known about that control word register. So anything you are going to implement, that value, that implementation will be loaded in control word register first, right? And this control word register will tell 8085 to implement that function that we have already uploaded in 8255. Okay, so the program loads the control word in the control word register of 8255 and make port A as output port, because in this DAC we have used the port A as output port, right? But you have to configure it first, right? So for configuration we have a control word register. Please recall that the 8-bit register for IO mode, for BSR mode, everything for mode 0, mode 1 and mode 2. So for using that concept, you have to configure the mode, you have to configure the port A, port B or port C, whatever you are using, right? And then these value will be loaded in your control word register by this programming code, right? Okay, so then the binary data for 0 volt is transferred to the port A. Here is the confusion. This binary data, once we are using 0, once we are using Vt, but Vt may be the value of 2, 3, 5, anything according to your choice, but these value will be loaded in your port A. But there is a one more constraint, that there is a half time period, because all the value is considered for half time period. The Vt is considered for half time period, means T by 2, and 0 is considered for another half time period, that is T by 2, and the total time period is T, right? Okay, so these binary data for 0 volt is transferred to the port A, and the delay routine is called to introduce a delay. Okay, so this is the main portion, the delay routine, because this is your subroutine call that you have to implement in your programming, that to call the delay, and after that delay again we are going to the rising edge, that means Vt. Again a month's delay we will call, and after that delay again there will be a falling edge, that is 0. Okay, so delay routine, there will be two delay portion, one is for Vt and one is for 0. So that's why I have written over there that binary data for 0 volt is transferred to port A, because port A is considered as an output port, right? And for that corresponding 0 value, once analog signal will be generated, and corresponding Vt value, one analog signal will be generated, right? So the delay routine is called to introduce a delay of half time period. Okay, and after this the data in port A is made equivalent to Vt volt, because 0 for 0 the programming function is already done, and after that it is the call for Vt. So after the data in port A is made equivalent to Vt volt, the delay routine is called again. Okay, so all this portion will be implemented in our programming by implementing a delay subroutine. Okay, so next portion is that the data for any voltage Vt, because I have generalized the voltage as Vt, but Vt may take any value. Okay, So these can be calculated by using the following formula. And what is the formula? Please note it down. The equivalent value of the Vt, that is equal to 2 to the power n minus 1 divided by the maximum output voltage, and whole this portion will be multiplied by Vt. Okay, so this is the main and mother formula for DAC for conversion part. Okay, and what is the n? N is nothing but the number of binary bits in the DAC input. Okay, and whatever the binary bits here, the what is the number? Number is nothing but 0 to 7, that means 8. PA0 to PA7, right? So this is 8. Okay, and what is your maximum output voltage? Maximum output voltage for this function, for this program, I have considered is your plus 5 plus minus 5 volt, or you can consider is your plus minus 12 volt also. Okay, and these will be multiplied by Vt. Now what is Vt? If you are going to implement, if you are going to design the Vt for plus 3 volt, then it will be considered as plus 3. If it is considered for plus 5 volt, then it will be replaced by plus 5. If it is plus 7, then it will be replaced by plus 7, and it will be going on, right? Okay, so what will be our calculation? Here I am going to generate the square waveform for 3 volt, right? So the what will be my what will be my equivalent value of the output of this 3 volt? This is equal to 2 to the power 8 minus 1, because n equal to 8, divided by the maximum output voltage. Maximum output voltage I have treated over here, that is 5 volt. So this is 5, and whole portion is multiplied by the 3, because we are designing it for 3. So this is the 153, but this is in decimal form, so you have to convert it to your hex form, because we are going to implement in the assembly language programming, and that without hex value, without hexadecimal number, any data will be incorporated in your assembly language programming. So any decimal value that you are getting from the calculation, you have to convert it first from your decimal number to the hexadecimal number, right? So the corresponding hex value is my 99H. So that will be implemented, and that will be treated as a control word register value. Okay, because this is the most important value that are going to implement, because our output voltage, that means Vt, we are going to design it for 3 volt, and for design to design it as 3 volt, my value is for control word register is 99. Okay, so now it's your programming part. So how to implement the whole thing in your programming part? So this is your assembly language programming. Introducing a delay. So first of all, just line by line, I have already written the whole explanation beside each and every line, but now I will explain each and every line once more. So first it will be please recall that whenever I taught the interrupt portion, interrupt of 8085 in the class, I just showed you to a sample program for configuring the ream and seam instruction, or 8255. In the 8255 part, I have already shown that what are the programming code to the how to take the value in controller register, and how to send the value to the controller register to some ports. What is the instruction? Because there is a sending instruction, there is a transferring instructions, the taking instruction and transferring instructions to the input port or output port. So the instruction will be out or in, but that portion I have already shown to you in your class, and that will be implemented in our subroutine programming also. The first line is MVIA 80H. Why it is 80? Because we are using port A, and the port address of port A, the by default port address is 80. For port B it is 81, for port C it is 82, and for control word register this is 83. Because here I have not extra adjusted the value to port A, port B and port C, so I will take the by default value, right? So it is taken as 80. So I have already written over here that load 8255 control word in the accumulator. So MVIA accumulator, right? MVIA means load this data to the accumulator and out to the control register. So move it to the control word register. So controller register will control the everything and will configure the port A as an output port. Clear? then MVI is 0 0. Why it is 0 0? Because we have a two voltage level. One is your 0, one is your VT, and for VT there the value is 99, and for 0 it's a simple 0. So that's why I have to take the value 0, because I have to transfer the value to the port A, and the corresponding that value analog signal will be generated, right? So the value is MVI is 0 0 for that portion. So out port A, because all we have to send to the port A, because port A is treated as your output port. So we are sending on the data to this port A and output the data to the port A where DAC is interface. Simple. Then we have to wait for some time, because the time duration, the time period, in between the two pulse, rising age and the falling age, that is T by 2. So we have to delay this program something. So for that portion we have to call delay program, the delay subroutine. So that's why I have written the instruction call delay. So call delay subroutine. So the delay programming will be called, and after delay programming the program sequence will be again converted to that portion where we left out, right? Okay, so call delay one more. So the delay, after this delay programming, again we will configure it for VT, but VT value we have already calculated it as 99. So MVIA 99, load the data corresponding VT, and out port A, simple, because we have to configure port A as an output port, so we have to send the data. And again it is called delay, because we have to convert it for 0, we will go it for 0, but before that we have to wait for T by 2 time period, and for that portion we have to call the delay subroutine, right? And next the instruction is jump loop. If all is going on, if all goes fine, then we have to exit the loop, otherwise we will again go to the portion where we will take the value 0 0, right? And what is your delay subroutine? Delay subroutine means the another counter will be taken as your count value. So this is treated as your register B, and load register with this count value, decrement it, jump if not 0, then again repeat. Here I have taken the indication repeat, and so this is your loop. So whatever value you are taking, that will be decremented, and that is your delay, right? And the repeat decrement until the required time delay is achieved, and if it is achieved, then the return to the main program, and if it is not achieved, then decrement the register once again. Okay, so this is the overall programming code, but this is some upper level of your EC403 that you have already learned in your class, but this is the beyond syllabus, but this portion is already there in your GATE syllabus, right? So please go through this, please try to understand that what are the instructions, what are the delay subroutine, and what are the formula for treating the VT as your choice value is 3 volt, 5 volt, 7 volt, or anything. So what are the mother formula, what are the implementation, what are the logic, everything. So please go through this. Until then, thank you.